The pseudo-quadrature mirror filter bank is also used for parametric surround coding and parametric high-frequency generation. The PQMF is a filter bank which has only near-perfect reconstruction, unlike the MDCT, which has really a perfect reconstruction. In the same sense, it is near para-unitary or orthogonal, which means that the synthesis filters are the time-reversed analysis filters. But it has the advantage that we have design methods to design filter banks with good longer filters with more overlapping time than we use with the MDCT. This results in improved nearby stop band attenuation. An often used configuration for this filter bank is to use 32 subbands with filters with a length of 512 or 640 coefficients, hence 16 or 20 times overlapping time. Compare that with the 2 times overlap in the MDCT. For that reason, we will now take a closer look at the PQMF filter bank. And you can also see the lecture slides of filter banks 3 that we explained when we talked a bit about the PQMF filters. We gave a short introduction in this video here. Let's go through the PQMF definition. The analysis filters of an N-band PQMF filter bank with filter length of L are defined given by this equation here. And you can go back to the previous lecture of filter banks that I showed before, and we'll explain a bit more the equations involved in the PQMF definition. But the analysis filters of an N-band PQMF is given here. And here the phase is defined here with some integer r. For convenience, we will omit some scaling factors. The synthesis filters, they are the time reverse analysis filters. So it's just given here. And you can see also this excellent book by Spanias, the audio signal processing encoder by Willy Press, and also these tutorials on PQMF modulation filters from Karma. And here we have this very interesting tutorials and information on PQMF cosine modulation filter banks. We will now do a reformulation of the PQMF for the case where the phase is given by this equation here, and L divided by N times the modulus of 4 is equal to plus or minus 2. And when we take this into consideration, we find that it is identical to our MDCT modulation function, which is a time reversal now on the right side of the equation. And we have this equation here. For the PQMF design, we can take the frequency response of the baseband prototype or the window function, and we have here that the h of omega is equal to the dTft of h of n, and then we need to find or optimize a function h of n such that it fulfills certain conditions. So the first very important condition is the attenuation. So the stop band attenuation should be high after the neighboring band to minimize aliasing. And it's given by this condition here. And we have a pass band from 0 to 0.5 times pi divided by capital N, and the transition band given by these intervals here. Another very important condition is the unity condition, the overlap region of two subbands. So the sum of the magnitude squared frequency responses of two neighboring bands should be close to a constant. And here is 2 times n squared, so we can achieve perfect reconstruction. And this is the unit condition here. And we have the positive frequency plus the flipped version of the positive frequency. So we have these two conditions, and we will optimize a function such that it fulfills these two conditions. Before we optimize these specific functions, let's just give an example of a Python optimization. So we will use some powerful optimization libraries that exist in Python to go through a simple example, and then we'll move on to optimize the PQMF functions so we fulfill those conditions. So to fulfill those requirements, we'll have an optimization problem, and Python has powerful libraries to find a solution. We will take a very simple example, which is to find the minimum of the function of two variables. And we have a function of x1 and x2, and this function is going to be sine of x1 plus cosine of x2. So what we do here is we define this function example with several unknown variables for optimization. And next we use the library psychoacoustic to find a minimum, and we'll use its function minimize. Here we are importing the optimize from scipy, and what we are doing here is that the x minimum is the optimize.minimize, and then we have this function example that we give here. We defined it here. We defined some certain methods, and you can take a look at the documentation of this function and you see all the available methods. And then when we minimize this function, and then we'll find that we obtain the minimum at x1 is minus pi divided by 2, given here, and for x2 is minus pi. So we succeeded in minimizing and using this optimization to find a minimum of a function of two variables. So this is the same principle that we are going to use to optimize a function for the PQMF filter. So now we will have a Python example of the PQMF optimization. And here we are defining this optimization function for a PQMF filter bank, where x are the coefficients to optimize, so the first half of the prototype h because of symmetry, and the ERR is the resulting total error. And see that here inside we are using both the unity condition and the attenuation condition. So here we have, for example, the sum of the magnitude square frequency response should be close to unity, or n, and we are having here the unity condition, and we also want high attenuation after the next band, and we have this attenuation, and the total error we are going to add the unity condition plus 100 times this attenuation condition, and this will return an error. So now we have a function to minimize, and we can use Python powerful libraries to minimize this function. And this is what we're doing here. We are now optimizing for 16 filter coefficients. So we have the x-min, and we are importing the scipy optimize as opt, and then we're using the minimize, the same what we did before, but now we have a different function to optimize, and it's this function that we defined here for the PQMF. We have a different method that we chose, and also we have these 16 filter coefficients that we want to optimize. So here we will have the resulting PQMF window function from the optimization, and it looks quite symmetric with a peak central. And here we have the resulting PQMF magnitude response. It's normalized to the peak, and we can see that we achieved almost 100 dB attenuation. So we get almost 100 dB stop band attenuation, which is much more than with the MDCT. We can verify the unity condition with this Python code. The unity condition is given here. We also used this unit condition before in our optimization, and we can verify, and this is what we are doing here. but we see that we get indeed a curve that is close to 2 times n squared equals to 32, but we have some deviation. So 32 is here, and we have some deviation here and here, and this shows that we get only near perfect reconstruction. It's important to observe that we obtain a 4-band filter bank with filter length of 32 taps, that means 8 times overlap. And the stop band attenuation reaches almost 100 dB, almost right after the pass band, which is much more than the attenuation that we get with the MDCT.